Hello friends, welcome to my channel. Let's have a look at problem 839 together, similar string groups. So in this video, we're going to share a method or solution based on disjoint set data structure. So this problem is marked as hard, but due to the statement or the scope of this problem, so you are going to find that solving this problem using disjoint set data structure is a natural thing. So the goal in this problem is to group similar strings into different groups. So in this problem, it defines in the first paragraph what does it mean by similar for two strings. And then in the second paragraph, it basically says that the similarity relation defined in this problem is not transitive. So in other words, if one string is similar to the second string and the second string is similar to the third string, it does not imply the first string and the third string are similar. So that's the main statement or the main task in this problem. So here we're going to share a solution using disjoint set data structure. So we'll mix the following correspondence or the idea. So first, we're going to use the find method in disjoint set data structure to create groups, and we're going to use the Uni method to merge groups, and if they were similar. So also we're going to use an attribute called nClusters to monitor the number of groups. So if we make a correspondence between the similarity group and the cluster in the disjoint set data structure for this problem, and then the cluster in disjoint set unit is corresponding to the group of similarity strings. So with that said, we guess that the solution or a solution to this problem using disjoint set data structure is right there. So the plan for this video is, first we're going to implement a class called DSU, disjoint set data structure. So the method we're going to implement are find here with path compression, and union here, union by rank. And then we're going to apply the data structure directly to the current problem, so which I personally think is very natural. And finally, we're going to print the group information so that we have a better feeling about this data structure and about the solution. So with that said, let's first look at the implementation for the data structure. So implementation of disjoint set. So abstract data structure. So I would choose to implement this data structure outside of the solution class so that we can use it for a general purpose tool as a general purpose tool. So first, let's implement that DSU. So let's look at the initialization quickly. So we're going to set the roots, which is the empty dictionary at the very beginning, and the rex also empty, and self nClusters is going to be 0 at the very beginning. So the root will basically find the representation of each cluster, and the rank is going to be the aid for merging the clusters or groups, and the nClusters attribute is going to monitor the number of clusters in the process. So this is the initialization and the roles of the attributes. So now let's look at the find method. So the find, so here S is a string as specified in this problem. So More precisely, we will see s in this problem, or for applying to this problem, s will be a string. So first, I'm going to consider if s is not already in the data structure. So if s not in self roots, so we're going to add it to self roots with itself being the root, and self rex so of s being 1, because it contains currently only the s itself. And then we're going to increment the number of clusters by 1. So in this case, we're also going to return its parents. So otherwise, so if s is already in the self root, we're going to make a chain of calls to retrieve the roots of s. So basically, it's a while loop. So first, I'm going to introduce a variable called result, initially s being s. Then we're going to check if result and its parents or its roots are the same. So if it's not, we're going to iterate, right? So here what we are going to do is basically we set the result equals self roots result. But before that, let me do a path compression. Self roots result. We're going to set the roots of result to be the roots of its root. So basically corresponding to apply this again. This plays the role of path compression. So yeah, there are different implementations for path compression. So you are encouraged to have a try. It's also good to know different formats of implementations so that we can use it according to different use cases. So with that said, if we exit this while loop, we're going to have a state that is result equals self roots result. Then we're going to return result. So that's about it for the find method. So now let's look at the uni method. The uni method accepts 2 strings. Then we're going to check if the 2 strings are in the same group or not. If they are in the same group, we do nothing. Otherwise, we merge them, and here aided by the rex. So for this purpose, let's first find their roots. Root 1, root 2 equals self find s1. This is the root for s1, and then this is the root for s2. So after we find the root, we're going to check if they are not equal. If they're not equal, we're going to do some work, otherwise we do nothing. So then we want to merge them together. And then the thing is that how do we merge? So actually we can do vanilla merge in some cases, but here let's do a merge aided by rec. So we are going to check the rec, self rex root 1. So if the cluster represented by root 1 is larger, so rex root 2, then we are going to set the root of root 2 to be root 1, self roots of root 2 to be root 1, and then we are going to increment the size or rect of the cluster represented by root 1 by that of root 2, self rex root 1 increment by self rex root 2. So this is the one case. In another case, basically we do the same thing but reverse the direction. So we're going to set the roots for root 1 to be root 2, and then increment the rex or the size of root 2 by that of root 1. So in this case, if root 1 does not equal to root 2, actually we merged 2 clusters, 2 distinct clusters. So the number of clusters is shrinked by 1. Therefore, we're going to decrement the clusters by 1. So that's about it for the union method. So I'm going to stop here for the implementation. Actually, we can implement some other hyperfunctions like get clusters. So we are not going to do that here. So let's maybe implement that here. So as we specified in the plan. So let's quickly do it. Get clusters or get groups. Self. So I'm going to initialize a dictionary, then iterate through the self roots. So for kv in self roots items. Then first I'm going to find the root, self find v. Then I'm going to organize the clusters. So if root in d, I'm going to d root add the current key to the set. Otherwise, I'm going to initialize the set to be a single element set consisting of this key. We're going to return this d, which represents the groups. So with that said, let's do the problem here. First, I'm going to initialize or instantiate the DSU data structure, and then we're going to iterate through the strings. N equals length of strings, just to track this information. So because the similarity relation here is not transitive, essentially we need to compare each pair. Though the similarity relation is not transitive, it's reflexive. In other words, if A is similar to B, then B is similar to A. So so in order to iterate and do the union, we need to find the criterion for doing the union. So that is, the two strings are similar. First, let's implement such a method. Is similar. So two strings S1 and S2. According to the constraint and the definition, so two strings are similar if there are and only two positions are different, which correspond to a switch. So, and also same strings are similar. So then we're going to count the different positions, right? So if it's 0 or 2, so it means they are similar. So for character 1, character 2 in zip S1, S2, then if character 1 does not equals to character 2, so we're going to increment count by 1, and then finally we are going to return if count equals 0 or count equals 2. So here one important assumption is that all the words are anagrams, so which makes this the is similar function valid in the current problem. So with that said, let's do the real work, and we're going to iterate, right, for I in range n. As the similarity relation here is reflexive, we're going to iterate for j in range I plus 1 to m. Then we're going to check if strings I or strings j are already in DSU or not. If not, we're going to make clusters out of them. So if strings I not in DSU roots, we're going to do find, right? DSU find strings I. So similarly for the string j. So actually we can put this here. It's a little bit better. So for I, then we're going to check this for j, right? If j not in this, we're going to do the find for j. Then afterwards, we're going to check if strings I and strings j are similar. So basically, if is similar. This is a method call. So self strings I strings j. If there are similar, so we're going to merge, right? So uni strings I, strings and G. So with that side, I guess that's about it. So after this while loop, for loops, so the final stage of DSU, and then we're going to track the number of clusters from the final stage. We're going to return DSU in clusters. So that's about it for this solution. So let's do a special case check first. So DSU object has no attribute. So funds. So here, let me do fund. So let's try it again. Oh yeah, it's good now. So here are two groups. So as we mentioned, let's also try to print out the groups. So let's print the DSU get groups. So this is the method, right? So let's do it. For example, for example 1, there are two groups. So one group is represented by tars, which consists of three strings: tars, arts, and rents. And the second group is represented by star. It contains star itself. So with that said, let's comment this out and do a generic case check. Yeah, it passes the generic case check. So that's all about this solution. So I'm encourage you to try Leetcode 305 using essentially the same code, or check out the corresponding video or other videos in the playlist. So that's about it for this problem. Thank you very much.